Welcome to the course on biostatistics and design of experiments. We will continue on this chi-square distribution as well as chi-square test. As I said, it is a very important test. It is almost like a binary yes no success failure type of thing. It is a continuous distribution, it is a skewed distribution, and it is very useful if I am comparing observed versus expected. I expect something, but I observe something. Is there a statistical difference in this observation? So, in such situations I use this chi-square test. Okay, so it is a distribution, once again to recall, it is a continuous distribution, but it is asymmetric. As the degrees of freedom increases, we can see the curve becomes more uniform, but originally it is right skewed. So, we can construct confidence interval, we can compare actual frequencies with the expected frequencies, we can compare fitted data versus the real model, sorry, with the real data. Okay, we can look at association between variables. Is like for example I said, is bad workmanship related to the work shift? That sort of situations we can look at. Is the poor results we get because of certain instruments, and that sort of comparative studies can be done using chi-square test. Okay, so the area under the curve is 1, and so when you are talking about say chi-square of 5, then this area will be the cumulative probability, that is between 0 and 5 of the occurrence. Okay. Now there is a table just like your T table, F table, Z table, and so on. We have a chi-square table also. In this column we have the degrees of freedom. Here we have for the two sided and here the one sided. This gives you the lower boundary on the left hand side of the critical value, because this curve is like this, right. So, you will have a lower boundary and upper boundary. Okay, generally we look on that side, upper side. Okay. So, this is a two sided, this is a one sided. So, obviously two sided 0.05 is one sided 0.025, two sided 1.1 is one sided 0.05. Okay. So, if the test statistics is greater than the upper critical tail critical value, then we reject the null hypothesis, or if it is lower than this lower critical value also, then we reject the null hypothesis. Okay, so, we can first do a test for seeing whether the sample comes from a population, the sample variance is coming from the population variance. So, if I have a sample set x1 x2 up to n, I calculate a variance s square. Okay, then I can compare it with the population variance of sigma square, the null hypothesis, and they are both same, the sample is same from the population, or alternate will be they are not from the same population. So, the test statistic is like this: chi square is equal to n minus 1, n is the data points, s square is the variance of the sample, sigma naught square is the variance of the population. Okay, then we can use this for testing goodness of fit. So, I observe something, but I expect something, observed minus expected square divided by expected, add up. So, here the null hypothesis observed is equal to expected, alternate will be observed is not equal to expected. Okay. Again we compare it, the test statistics with the table, and then if the test statistics is greater than the table critical value, we will say the null hypothesis can be rejected. Okay. So, it can be used for dependence, interdependence, like I said, whether poor workmanship is related to the type of shift, if is poor results related to the instruments we use, that sort of situation. So, let us look at a problem. 3 different grades of product is expected from 2 machines. There are 2 machines, 3 different grades of product. Okay. What is the H naught? The null hypothesis, they are independent. Alternate is these two are related with each other. Okay. We observe on machine 1 grade A 3, grade B 9, grade C 8, whereas sorry we observed 3 9 8, but expected is 4 8 8. Same thing on machine 2, we observed 7 11 12, but expected is 6 12 12. Now I want to look at the hypothesis, the null hypothesis, that the variables are independent, that means the grades are independent of the machine which we use, but alternate will be they are related with each other. So, what is the test statistics? Observed minus expected square divided by expected, 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 right. So, you get a chi-square of 0.625. Now, if you go to your table 0.05, how many degrees of freedom? We have 2 machines. So, 1, we have 3 grades, 3, that gives you 2. So, totally 2 into 1 is 2. So, we look in under the column of 2, okay, and then we say 5.99 for a 95%. So, we expect the table is 5.99, test is 0.625. So, null hypothesis cannot be rejected. So, the grades are independent of the machines, okay. Very nice problem. Okay, let us look at another situation. We have say incidence of 3 types of malaria in 3 in tropical regions, Asia, Africa, South America. Malaria is a very serious problem. There are different types of malaria, okay. Malaria A, malaria B, malaria C, okay. So, the malaria A is happening 31, 14, 45, malaria B is 2, 5, 53, malaria C is 53, 45, 2, right. Okay. So, I want to know whether it follows the expected, okay. This is the what is observed, okay. The expected, we expect all the malaria either to be same, that means the H0 will be the 2 categorical variables, that is type of malaria versus the type of continent should be independent, there should not be any relationship on that actually. The other one is the alternate will be these 2 variables are related to each other, okay. So, we if there are 90 cases, we expect that, okay, all of them should be there in all the countries, okay, because we do not expect any sort of correlation or relationship in this entire situation, okay. So, this is the observed, expected is it is equally probable in all the 3 continents, malaria A, malaria B, malaria C should be equally probable, that will be what is called expected. So, observed is this, so observed minus expected square divided by expected. So, we should be able to get the test statistics. In this particular problem we get 125.5, okay. So, this problem we get it as 125.5, and degrees of freedom we have 3 continents. So, 2 is the degree, 3 types of malaria, 2 is degrees of freedom for type. So, 2 into 2 is 4. So, we go to 4 degrees of freedom and 95%, okay. So, let us look at the table, 4 degrees of freedom and 95%. So, we get 9.49, okay. So, 9.49, yeah, 9.488, okay. So, when you do that we will get test statistics is 125.5, the table is 9.488, okay. So, we can reject the null hypothesis. What is the null hypothesis? There is no relationship between the type of malaria and the continent location. So, we can reject. So, there seems to be some sort of a correlation on type of malaria and the type of and the location or place from which it was observed, okay. This is how we need to do this type of problem of where we have the observed versus expected, okay. Now, as I said, Excel also can do, there are 2 types of functions in Excel, okay. There are 2 types of functions in Excel I mentioned. One is the chi test, where you give where in chi test we give okay, we give the actual value, then we give the expected value, okay. Okay, so let us look at this previous problem of grade where we say we expect okay. observed is 3, 9, 8, 7, 11, 12, whereas expected is 4, 8, 8, 6, 12, 12. Okay, so how do you do this problem? Chi test. So the actual expected. So the actual and the expected. So we get a probability of 0.98. So obviously null hypothesis cannot be rejected. You understand? So that is what we got from our calculations also, or we can say chi in 0.05, the degrees of freedom here is okay, 3 gives you 2, 2 machines gives you 1, so that gives 2, so it is 5.991. okay. So we need to look at this 5.99 here actually, right. So the inverse, chi inverse gives you exactly like your table, it gives you the chi square value and that is the critical value, whereas the chi test gives you the probability for your problem and gives you the probability given the observed and the expected. Okay. So we can do, now let us look at this problem also using Excel and see whether we can do it using Excel. Okay. So this is the observed, sorry, observed is 31, 2, 53, 14, 5, 45, 45, 53, 2, okay. Whereas when I say expected, how do I calculate the expected? It is a bit tricky to do that actually. We will look at this type of problem later on actually. We need to calculate expected is 86 divided by 250 into 90. Okay. So it will be like 86 divided by 250 into 90, that is you expect 30.96 because 86 is the summation of this, 250 is your grand total, the summation of this is 90. So you take that same ratio, you will get it as 86 divided by 250 into 90. Okay. So for this, what is that ratio? 86 divided by 250 into 60, 86 divided by 250 into 60. Okay. What about this one? This will be 86 divided by 250, 86 divided by 250 okay, into 100, that is 34.4. That means I expect a 34.4, I expect a 20.64, I expect a 30.96. You understand how to get this, each one of them. So if I want to get this, I say 86 okay, divided by 250, that is the grand total, multiplied by 90. So it is just a question of ratio. So if I want to get this, if I want to get this 53, I will say 86 divided by 250 into 100. Okay. Then if I want to get this, the expected, what do I do? 64 divided by 250 multiplied by 90. The next one will be 64 divided by 250 divided by 250 multiplied by 60. The next one will be 64 divided by 250 multiplied by 100. The next one here will be for equivalent to 45. So what do I do? 100 divided by 250 multiplied by 90. The next one will be 100 divided by 250, 100 divided by 250 multiplied by 60. Then next one will be 100 divided by 250, 100 divided by 250 multiplied by 100. Understand? So that is how we got, sorry, 100, there is a minus term here, I made a mistake. 100 divided by 250 multiplied by 100. So, we can cross check by doing summation, should come to 250, and this also should come to there is a mistake there somewhere. So, obviously this also should come out to be 250. So, it is not come out to be 250. So, obviously we have made a mistake. So, the first term here will be 86 divided by 250 multiplied by 90 and so on actually. Okay. Divided by 250 into 90, then next one will be 86 divided by 250 multiplied by 60, then 86 divided by 250 multiplied by 100, then next one will be 64 divided by 250 multiplied by 90, then 64 divided by 250 multiplied by 60, then 64 divided by 250 multiplied by 100. So, obviously there is a mistake I have made here. So, I put minus here, so that is the mistake. Okay, so I got 250 in both the cases, that is very good. So, I can use chi-test, CHITEST, comma. So, you get a very small probability, which means that we can reject the null hypothesis, which means that null hypothesis there is no relationship between the location or continent and the type of malaria. Same thing I got here, right. I rejected. Now, so by using a chi-test I am able to reject the null hypothesis. Now, same thing we can do by chi-inverse also. Okay, I will say 0.05. The degrees of freedom as you know I said is 4 because 3 continents and 3 types of disease. So, 4. So, it comes out to be 9.48, right. So, 9.48. So, from the chi-test command we can reject the null hypothesis. Okay, so we can also do it using your graph pad, because of as you can see we have the commands for graph pad here also. We have the chi-square here, right, chi-square, or here we have the chi-square which can do this type of calculations. Okay, so we can do chi-square exactly. So, chi-square from a probability, this is equivalent to a chi-inverse, whereas this is equivalent to a chi-test command. So, you can see this chi-test command. Okay, so so it is exactly like the chi-test command, where it gives you the p value, or in this particular case it will give you the, okay, given the probability it will give you the chi value. It is exactly like chi inverse. So, even in your graph pad we can do that. So, the chi-test and the chi-in command available in Excel, and even in graph pad we use these two. Okay, we use this to do that actually. Okay, so let us go back to our problem, and so we will say we will reject the null hypothesis that there is a association between these two categories or parameters. Okay. Okay. So, when one important point you need to consider is, generally if you are involving only 2 categories, for example, if I am doing a 2 by 2 contingency table, especially for 2, then there is something called a Yates correction, because chi-square distribution is continuous. Okay. Whereas when we use 2 categories, yes, no, or success, failure, or drug working, not working, obviously we are not able to as such do good justice, because in a 2 category system it is like a discontinuous data or integer data, whereas chi-square is a continuous data. So, in such situations you need to subtract something called the Yates correction. Okay. So, this is called the Yates correction, where you just do the expected minus observed. Okay. That is, you calculate expected minus observed, then subtract minus 0.5 from that. after that you square it up and then divide by, okay, that after that it is all same expected, no problem. Okay. So, if you look at the normal, okay, we used to have observed minus expected square or expected minus observed square, okay, divided by expected. So, what you do is you just subtract minus 0.5, this is valid only when you have something like a 2 by 2 type of contingency table, okay, and then in such situations you just instead of this term you subtract from minus 0.5 from there, and then after that you square it up and divide by expected in the denominator. Okay. So, that is all, that is the only difference which you need to consider when you are going to give age correction. This is valid when we are talking about 2 by 2 type of contingency table, where we are talking in terms of integers, especially drug working, not working, S no, not and S, that sort of situations we need to use it. So, we look at some problems where we use age correction, but one important point is when the data is negative, that is when you calculate expected minus observed negative, we cannot further subtract from minus 0.5 into that. That is very, very important when we are talking in terms of age correction. Okay. That means when expected minus observed is already negative, we cannot again do more negative and take it out below 0 value, that is not permitted actually. Okay, let us look at a problem which is a 2 by 2 sort of situation, because we are talking about a drug working on a set of patients. So, because of the drug, patients either die or alive, we expect some data, whereas we observe something else. So, we need to look at whether there is an association. So, in such a situation we are also applying the age correction as well in this particular problem. Okay. So, look at this particular problem. In a disease with 40% known mortality, a drug is given to 17 patients and only 3 died. Okay. So, 40% were known to die, that means 17 patients we expect 6.8 to die, the remaining 10.2 not to die, but we observe 3 to be dying and 14 to be alive, right, 3 plus 14 is 17, 6.8. So, is the drug effective? We need to find out. Okay. What do we do? Expected minus O, that is E minus observed, 6.8 minus 3 is 3.8, okay, expected minus observed. Then we do a correction here, okay, and then that is we subtract it by 0.5, that comes to 3.3. Okay. Then once you calculate the difference between the expected and the observed, you use the absolute value and then subtract minus 0.5 from there, that is the age correction, and that is why you get the corrected E minus O, that is expected minus observed, to be the same on both sides, because we are taking the absolute value and then subtracting minus 0.5. After that you square them and then you divide each one of them with the expected, you add up to get expected minus observed corrected square by expected. Now, this is what you get, 2.67. Now, this is at 1 degree of freedom, because we have die alive 2 states. So, we have 1 degree of freedom. So, if you look under 1 degree of freedom, okay, for a p is equal to 0.05 for a one sided test, we get the table chi-square as 3.84. Now, your statistics is 2.67, okay, and the table is 3.84. So, you cannot reject the null hypothesis. So, we cannot conclude the drug is effective. Okay. So, you understand this age correction here. So, remember that you do the age correction, that is you subtract minus 0.5 from the absolute value of expected minus observed. Okay. Thank you very much.